Hello viewers, welcome to our course Photochemistry. Under this heading, we are discussing another photochemical reaction called Paterno-Büchi reaction. This is a photochemical reaction between aldehyde or ketone and alkene or alkyne. So if it is alkene, then the product is oxytine. So this 4-membered ring with one oxygen. So this is a cyclic ether type product. Oxytane is formed. So this is a simple case when the alkene is simple alkene like ethene. So, but when here the substituents are involved, then the products are different. So we will discuss it later on in the detail when here the substituents are attached here. This reaction is very similar to 2+2 cycloaddition of alkenes to form this cyclobutane type product. So this reaction, when we use here substituted alkene, for example this one cis alkene, then reacts with this ketone, the product is trans. Trans is the major product here, whereas the cis is the minor. When the alkene is trans, here these two methyl groups are electron donating groups through their positive inductive effect. So the product is here, the cis is the major product. When strong electron withdrawing group is attached on this alkene is cis. Here the nitrile is attached, which is very strong electron withdrawing. So the product is again major product is cis alkene. So this we will discuss in detail that why the stereochemistry, how the stereochemistry is controlled. So we will discuss it in detail. So here we go. Here we have simplest alkene like ethene. Here this one is cis alkene with the electron donating methyl groups, and here this alkene has two cyano groups. They are strong electron withdrawing. So if you see it's a simplest alkene, we draw like that, homo and LUMO. But when electron donating group is attached, make this homo at higher energy than this simplest alkene. So this homo is at higher energy. Same is the case as compared to the LUMO of ethene. This methyl donating groups make the LUMO at higher energy as well. So when it is at higher energy, it means that this is more reactive. This alkene is more reactive as compared to this one, simplest ethene. So, but when electron withdrawing group is attached, then you can see if we compare with the ethene, then this homo is at lower energy than this simplest ethene. So this make this alkene less reactive. So if you see the energy wise, energy is increasing in this direction. So this homo, when electron withdrawing group is attached like nitrile or cyano group, this one, so this make the homo at lower energy as compared to simplest ethene, whereas when electron donating group is attached, then make this homo at higher energy. If you draw the molecular orbitals, sigma, pi, non-bonding. Non-bonding means the electrons in the lone pair. So electrons in the lone pair are easily available to electrophile. If you see the reactions, then the electrons in the pi bond, this is a simple pi bond, these are the bonding. These are three orbitals on the bonding, these two are anti-bonding. So electrons easily reacts with when it is present in the form of lone pair, and then least reactive is that with when the electrons are present in the sigma bond, they are least reactive. So with the pi bond, then again it's lies in the middle. Same is the case here. Make this when electron donating groups are attached, make this alkene more reactive, because its homo lies at higher energy than this homo of simplest ethene. Same is the case when electron withdrawing group is attached, like this cyano group, it makes the homo lies at lower energy, so make it this alkene less reactive. So we will discuss this one, that how the mechanism of the Paternò-Büchi reaction operates. So here we discuss as we are discussing the mechanism of this reaction. This is the first case when the alkene has electron donating groups. This makes the alkene at higher energy. So alkene energy is high as compared to the carbonyl compound. So in the presence of the light, this bond is cleaved, this pi bond, and gives two radicals. So these two radicals, they have opposite spin here, so they are excited in the presence of light. This is the excited state of this carbonyl compound. So with these two radicals, they have the opposite spin, these two electrons. Spin of this electron is different from opposite to this electron. So in this case, intersystem conversion occur. If in intersystem conversion, now you can see the spin of this electron is changed. Yeah, this is I'll explain in the Jablonski diagram, where if the electron is excited to singlet, then it's intersystem crossing, and then spin of the electron is changed to triplet state. So here you can see this spin of this after intersystem crossing, spin of this electron is changed. So when this combined with this alkene, here you can see this pi bond is broken in these two radicals. So you can see this radical and this radical, they form the bond. So bond is as we discussed in case of carbenes, bond is only formed when this spin of the electrons are opposite. So this as you see, this radical and this radical has opposite spin though. So single covalent bond is formed here, and then you can see on the single bond here we can rotate. This single bond can be rotated. So this, if we make the bond here, then this single bond can be rotated, and this after the rotation you can see the stereochemistry is changed. Now here you can see this, if this is methyl and this methyl is above the plane, and here you can see it is below the plane. So here, but this here after this rotation around the single bond, here you can change stereochemistry change, but the spin of the electron remains same. So in the presence of light, spin inversion occur. So we can spin inversion can occur on this here you can see this written here. Spin inversion here changed. Now they have the two electrons have opposite spin. Now we can make the bond. So this after making the bond, you can see we get this trans as the major product. So this is the explanation. When alkene has more energy, electron donating groups are attached, then carbonyl compound, then intersystem conversion occur, and then intersystem conversion we can single bond rotation. So we change in the stereochemistry, but the spin remains same. Spin inversion occur. So at one of these free radical, so that this radical and this radical have opposite spin, then we can make the single covalent bond here, and they have the opposite spin. So this bond, and now the opposite spin, we can make the bond here, and we get this trans as the major product. This is the other way. When cis is the major product, here you can see this transition state. When in the photochemically, this both the electrons you can see have opposite spin. We can make this cis is the minor product here. So this is when the alkene is trans. Here again this alkene has trans methyl groups. So energy of the alkene is greater than carbonyl compound, and when the presence of light, now here when alkene is trans, the product is cis is the major product, whereas the trans is the minor product. Again the same intersystem conversion occur, and then the rotation around the single bond occur, we change the stereochemistry, and later on the spin inversion occur to make this cis as the major product, as we explained it previously in the previous example. So here this is another case when electron withdrawing groups is attached to the alkene. In this case the energy of the carbonyl compound is greater than this alkene. Then there is in the presence of light, this trans is the major product in this reaction. So this is the second case. So this is the Paternò-Büchi reaction of carbonyl compound aldehyde ketone with alkyne. So when alkyne is used as starting material, here you can see in the presence of light, this pi bond is undergo homolytic cleavage. One radical is on here, make this here oxygen radical and this carbon radical, and then same is the homolytic cleavage with that pi bond of the triple bond. One of the pi bond of triple bond undergo homolytic cleavage to form this radical on carbon and radical on this one. Then these radicals combine to form this one. Here the double bond comes instead of single bond, because this is here we're using the alkyne as in starting material. So then this ring is highly unstable, so this undergo ring opening to form this alpha beta unsaturated carbonyl compound. So when this Paterno-Büchi reaction with alkyne, we get this conjugated carbonyl compounds as product. So this is another example of Paterno-Büchi reaction. In this case, we have this type of alkene and this type of the carbonyl compound. So in the presence of light, so this if this CH2 of this alkene makes the bond with the oxygen. So this CH2 radical and this oxygen radical, they make the bond, and this carbon of the carbon radical and this carbon radical of carbonyl compound makes bond, then we get this product. So if vice versa, if we flip it, if you flip this carbonyl compound like this, so if this carbon and this carbon makes the bond and this carbon and this carbon make the bond, we get this type of oxytane derivative. So this product is different from this product. So which one is the major product? So question is that which one is the major product? So in this photochemical reaction, it depends on the stability of free radical. So one is if the radical is stable radical, so in other way around, if radical is unstable, it is more reactive. So unstable radical more reactive. If it is more reactive, then it will it react quickly. So this is the answer. Now if you see the radicals, this CH2 radical is primary radical, and this radical on this carbon, it is tertiary. So this is tertiary radical, this is primary radical. So tertiary radical is more stable than primary radical. So this radical, and if you see here on this radical, which is you can see there phenyl is attached, so this is like benzylic radical. Through resonance, this radical can be stabilized into the phenyl ring. In the previous lecture, I also explained that how the benzylic radical is stabilized through resonance. We draw the resonance form. So this is there the two phenyl rings are attached, which make this radical more stable as compared to this one. So in this case, this radical is less stable and this radical on oxygen is less stable. So they make the bond quickly. So if we make this product, this bond is formed quickly. Later on, these two radicals combine to form the product. So this one is the major product. So this is the major product. And this is the minor product. So this one is the minor product. So this is another example of the Paterno-Büchi reaction. Here we have the carbonyl compound in which the two phenyl groups are attached, and this is cyclohexadiene. So this in the presence of light, they undergo the excitation to form these this carbonyl form this radical on here. If this undergoes cleavage, homolytic cleavage, then this radical on free radical on oxygen and free radical on this carbon. So which radical? So this oxygen radical can combine with this radical here on this carbon, or this radical can combine with this radical here. So it depends on, as we discussed in the previous example, this depend on the stability of the free radical. So if you see here, this free radical, this is they have the two phenyl groups are attached. So this radical can be stabilized through resonance these two phenyl groups are attached. So this is like benzylic type radical. So this radical is more stable. So right here more stable. This oxygen radical is less stable. So if you see here, in the case of this cyclohexadiene, this two radicals here, if it undergoes homolytic cleavage, this double bond, so we get the one radical here and one radical here. If you see, this radical is more stable because this radical is in conjugation with this double bond. This is just like allelic type radical. We already discussed the resonance form of this allelic type radical. If this comes here, this radical comes here, then this radical goes here, we can stabilize this radical through resonance. So this is more stable, this is less stable. So less stable react first. So we make the bond between these less stable radicals. So we make this bond first here, less stable, more reactive. Then this stable radical form the bond. We get this as the major product, while this one is the vice versa. This one is the minor product.